Thank you. My plan is to just remind you about the LDE mission, about the LDEX instrument, and then spend most of the time about our science results, especially the large piece, which was we are struggling with understanding of finding really, really large positive charges on small dust particles. That's the mission. We started out, spent a month in the altitude range of 200, 250 kilometers or so, and eventually dropped down and spent over 100 days, 150 days or so, in the altitude range of 50 to 100. And towards the end of the mission, we started to dip really, really close to the surface. LDEX is an impact ionization dust detector. A small particle comes in with a typical speed of about 1.6, 1.7 kilometers per sec. That is sufficient to make a plasma puff. Electrons and ions are repelated. An electric field is set up to collect the ions in a multi-channel plate and the electrons on the target. And then the way we use that is compare the waveforms that for the collecting the ions and the waveforms collecting the electrons that we gathered at the University of Colorado Dust Accelerator to similar waveforms that we see in space, and that will enable to tell you at least the mass, perhaps even the speed of the incoming dust particle. This is what we found as a function of time. This is the average impact rate of particles that are bigger than 0.7 micron and much more abundant, of course, the particles that we found with radii bigger than at least than 0.3 micron. So here it is. The impact rate goes roughly at 1 per minute or 1/10 of a minute. It is, we are continuously bombarding, even though it being collecting or noticing dust impacts. And there are special periods, of course, that Jamie Salai will address in a talk or two after this one. So here it is. There is a permanently present, continually fluctuating, replenished dust cloud around the moon. Each dust particle typically has a lifetime of 10 minutes, but it's being bombarded. The moon is being continually bombarded, so the cloud is there all the time. If I were to average out that we have seen and give you kind of the average cloud around the moon, this is the dust density of small particles bigger than 0.3 micron in radius as a function of height. This is our expectation of the Krivov model that you heard about a couple of minutes ago, that simply assumes the size distribution and the speed distribution are independent from each other, and both of them is described with a simple power law. That model was actually developed for the icy moons at Jupiter, so one might or might not be surprised that it kind of partially works at the moon, and that was certainly a kind of an issue that we brought at the proposal time, that we have no clue how to compare an icy surface and the dust production from an icy surface to the surface of a regolith covered body. If I add up all the mass that hangs in the atmosphere or in route going up and down, it's about 120 kilogram is hidden in dust at all times, which is, by the way, a tiny fraction of the lunar atmosphere, less than 1% of what is the estimate for the total mass of the lunar atmosphere. If you make really simple assumptions, and we could go back and justify, is that most of the dust particles that we detect roughly are nearby their turning points. Like, remember the beach ball at your summer vacation, you toss it up, it slows down, stops, and falls back. If you make a simple energy argument, how fast you should be started, that we get the distribution in number of impacts as we have seen it, it turns out that the parallel assumption for speeds seems roughly all right. For speeds about 400 meters per sec, but we are lacking really, really small particles, and that's why close to the surface we detected much smaller number of particles than expected based on the Krivov model. Of course, because the regions we visited, that doesn't tell me that what are the highest speeds. There could be particles that are enormously faster than the ones I can testify that we detected. This is if I actually shy away from making an azimuthal average. Here is the lunar dust cloud as we look down. That's again the average for the entire mission. And you notice immediately there is a huge enhancement in the direction of the motion. And then we can argue about what is that due to and whether that's cometary or asteroidal dust, or expectation that is best explained by a large population of particles with with very large inclinations that come more or less and give a head-on collision. So they're almost retrograde orbits. So at these regions, you can have impacts 50, 60 kilometers per sec, and the dust production is a very sensitive function of the incoming speed. This is a waveform I've showed you before. Most 99.999% of our impacts look like this, nice and smooth, and we could read out the impact charge and the target charge. Sometimes we have waveforms like this. The ion signal looks exactly before, and the electron signal that we are collecting on the target has a huge dip that is preceding this. And we have seen this countless times at the accelerator, and our understanding that these are actually the charges the particles carry before the impact. We have a nice hemispherical target. Remember, Gauss is low. I'm going to bring in an extra charge, and that will polarize, that will make an image charge on the target that we measure. Negative charges, the electrons, give you this big jump up. So these particles are positively charged. Huge positive charges are detected by LDEX. Not a whole lot, maybe a couple hundred throughout the entire mission out of 150,000 of total impacts that we detected. But it's really curious. So then one would immediately start looking at what are the charging processes I know about. Of course, UV lights, that is certainly a candidate. And it turns out that UV exposure, and the color code here tells you the grain potential. The grain potential is simply just the charge divided by the radius of the grain that we detected. And there is not a whole lot of dependence on whether you are in the lit or the dark side around the moon. That's curious. Then you would say, all right, the plasma environment is quite different as the Earth and the moon is going, the moon goes around the Earth. And then you could look at periods where you are in the magnitude tail versus periods that you are in the solar wind. And here it is as a function of the R angle of the moon around the Earth. And I don't see a whole lot of dependence. And I see a whole lot of particles that are typically a micron or a few micron in radius. And they carry a surface potential of about 100 volt, positive. That's really curious. So then one could argue what happens? How do these particles acquire their charge to begin with? So we know about impact plasmas, and we could read up in the literature what happens in a small explosion as you have an expanding cooling plasma cloud. And I apologize because the plot on the right is from an old calculation of a hot plasma column, which is a discharged plasma, what happens in the dust particle. But it's good enough to point out to you that most likely I would expect negative charges. The electrons typically are much hotter initially than the ions. They thermalize in a very short amount of time. They expand, cool, and everything will recombine, so the plasma will vanish. And along the way, you could calculate the expected equilibrium potential on the dust particles. And it's really, really hard to argue for a plasma setup that will give you large positive charges. Then you could say, all right, so charging is a problem. How about discharging? Because it takes 5-6 minutes to rise to the height of the spacecraft. Even if I give you such an enormous initial charge, how do you keep it that long? So what sort of discharging times do we look at? And the plot on here is just shows you what happens to a micron-sized particle that is uncharged and put into the solar wind at 1 AU. UV charging will dominate, but I want you to pay attention to the electron current, which is initially is about 30 electrons per second will be captured from the solar wind. And I can use this to give you a quick estimate. Whatever charge you start, if I want to discharge you, if it's a large positive charge, I have to collect electrons. If you have a large positive charge, there's an enormous enhancement in your Coulomb cross-section, 1 plus E5 over KT. That could be a factor of 10, maybe even more. So the discharge time turns out to be comparable to the rise time. I don't know how on earth you didn't lose this charge. I don't quite know how that is. Maybe I'm making a mistake in my estimate how fast you go. Maybe there are some particles that are much, much faster and reach this height, and then they can remember what is the charge that they started with. Of course, charging has another random element. It's a stochastic process. It's okay to calculate the random, the standard charging currents for a spacecraft, for a large object. Fluctuations on small particles become much more important. And it's quite likely that some lucky ones could get away with an enormous charge, not what I expect from a simple charge balance calculation. So Here we are. Actually, this is all I have to tell you, other than just to summarize that we have noticed permanently present cloud that is already published. Please look up in the literature. A tiny fraction of them seems to be carrying an enormously large positive charge. Both the generation and the retention of these large charges seem to be problematic when I look around and look what sort of processes I recognize in the environment. And I have to default on something more exotic, possibly, like the breakup process or triboelectric charging that would possibly give you these large amount of charges. And it's not as bad as one would immediately think about it. If I have a 100 micron particle excavating a hole that is 100 micron cubed in volume, and I argue, let's have just a whole bunch of tiny particles and a couple of big ones. What sort of collision rates can I get out? And then argued, typically, even if a like material, little guys will steal electrons from the big guys. Collisional processes, like in a volcanic plume, like in dust devils, in many other cases, people did notice that even if you have the same type of material, little fellows steal electrons from the big ones. So if you have enough collisions and little guys steal enough from the big ones, and this is an insulating material, so they can probably retain their charges and keep accumulating it, it is possible that we could generate these large positive charges that LDEX observed. Thank you.
Adrian Brown, Study Institute, thanks for a great talk. Is it possible that you're seeing some dust that hasn't actually interacted with the moon? What are the chances of that?
Slim to none.
And can you explain why?
Right. So LDEX, by design, is pointing in the RAM direction. Let's look at an incoming interplanetary dust particle, which probably comes somewhere in the region of 15, 20 kilometers per sec. So my effective sensitive area is really, really small. In the data set, we do have a handful of impacts that saturated everything. So maybe there are a couple ones that are not from the moon. But then I have a problem, because in interplanetary space, your charge should be 3-5 volts positive, which is much, much smaller than I measured.
Okay, Derek. Excuse me. Derek Sears, NASA Ames. I'll ask you the question I wasn't able to ask just now. If the meteoroid particles coming into the moon were water-rich, they're just ice with a little bit of dust in them, would that affect your thinking at all?
So an incoming particle, be ice or dust, has an enormous yield. Every gram of incoming at this speed generates a kilogram of outgoing matter. So the probability that I somehow recapture a small amount of the initial incoming particle that somehow is returning on an outbound trajectory, I think it's small, but I'm thinking on the top of my head, I might be off. I don't have a good answer for you.
Okay, just for fun, if there's water in the surface.
Sure, but I still have a charging problem regardless of the material. I have to look back how, these charges are generated in clouds and what sort of processes that would... All right, then whoever is stolen the electron from are the ones that I'm detecting. I forgot to tell you, of course, it is hard or difficult, even if negatively charged particles would exist. The way the instrument works, I would have a hard time noticing it. So it could be that they exist, but I might not notice them.
Hey, Mihaly, let me ask a question. Is this small fraction of large positive grains, are they part of a larger cluster? Because you mentioned sometimes you get these big bursts of, 50 grains all at once. Are they buried in the middle of that?
There was one, the Northern Towers early on, that a handful of these emerged, but then they were dispersed throughout the mission. That was particular because we noticed that primarily in the big particles. I don't know why that is. I don't know why that stream is different than the others. Maybe because of its location was kind of far from our ground track on the surface. There is a little. If I were to plot this as a function of time, you would notice during the Northern Tower, it's a handful of events happened then, and the rest was dispersed throughout.